Welcome! In this session, we will explore an exciting problem titled Number of Subarrays with Odd Sum. We'll break down the problem, analyze different approaches, and understand how to solve it efficiently. Let's dive right in. In this problem, we are given an array of integers called ARR, and our goal is to determine how many subarrays within this array have an odd sum. A subarray is any contiguous portion of the array, and its sum is simply the total of all the elements within that portion. Since the number of subarrays can grow very large, we are required to return the result modulo 10 to the power of 9 plus 7 to ensure the output remains manageable. The input to the problem is a single array of integers, and the output is an integer representing the count of subarrays with odd sums, adjusted by the modulo operation. Let's explore this with a few examples to better understand the task. Consider the first example where the input array is 1, 3, 5. To find the subarrays with odd sums, we can list all possible subarrays and calculate their sums. For instance, the subarray 1 has a sum of 1, which is odd. The subarray 1, 3 has a sum of 4, which is even, so it does not count. Continuing this process, we find that 3 has a sum of 3, 3, 5, sums to 8, 5, sums to 5, and the entire array 1, 3, 5 sums to 9. Out of all 6 possible subarrays, the ones with odd sums are 1, 3, 5, and 1, 3, 5, giving us a total of 4 subarrays. Therefore, the output for this example is 4. Now let's look at the second example where the input array is 2, 4, 6. Here, we notice that all the elements in the array are even. When we calculate the sums of all possible subarrays, we find that every sum is even, regardless of the length or combination of elements taken. For instance, 2 sums to 2, 2, 4 sums to 6, 4, 6 sums to 10, and so on. Since there are no subarrays with odd sums in this case, the answer is 0. Finally, in the third example, the input array is 1, 2, 3, 4, 5. The subarrays with odd sums include 1, 1, 2, 3, 1, 2, 3, 4, 5, 2, 3, 3, 3, 4, 5, 4, 5, and 5. When we count all of these, we find that there are 8 subarrays with odd sums in total. This gives us the output of 8. Additionally, we need to account for constraints. The array length can go up to 10 to the power of 5, and the values in the array can be very large, so our solution needs to be efficient. For edge cases, if all elements are even, the result is 0, and if all elements are odd, subarray sums will alternate between odd and even. This highlights the importance of optimizing the approach for large inputs. To start, let's consider the brute force approach. The intuition here is straightforward. We generate all possible subarrays from the input array and calculate their sums one by one. If a subarray's sum is odd, we increment a counter. The algorithm involves iterating through all possible starting indices of subarrays and, for each starting index, iterating through all possible ending indices. Then, for every pair of start and end indices, we compute the sum of the subarray and check if it's odd. If it is, we increment our count. Finally, we return the total count of odd sums, ensuring the result is taken modulo 10 to the power of 9 plus 7 to satisfy the problem constraints. Analyzing the complexity of the brute force approach, we see that it has a time complexity of n squared, where n is the length of the array. This is because of the nested loops required to compute sums for all possible subarrays. In terms of space, this approach is efficient, using only O1 additional space since we don't store any intermediate data structures. However, the drawback is clear: the quadratic time complexity makes it impractical for large arrays, as the number of computations grows too quickly. To address this, we turn to an optimized solution using prefix sums and modular arithmetic. Here, the key insight is that we can use the parity whether a number is odd or even of the prefix sums to determine whether a subarray sum is odd. Specifically, the difference between two prefix sums is odd if the subarray sum is odd. By leveraging this relationship, we can avoid recomputing sums for every subarray and instead use a running count of odd and even prefix sums to efficiently calculate our result. With the optimized approach, we begin by initializing two counters, odd_count and even_count. Initially, even_count is set to 1 to account for the prefix sum starting at 0, and odd_count is set to 0. We then maintain a prefix_sum variable, which starts at 0 and updates as we iterate through the array. For each element, we add it to the prefix underscore sum and check its parity. If the prefix underscore sum is odd, we increment the result by even underscore count, representing the number of subarrays ending at the current index with an odd sum. Conversely, if the prefix underscore sum is even, we increment the result by odd underscore count. Finally, we update the counts of odd and even prefix sums based on the current prefix underscore sum. The result, once computed, is returned modulo 10 to the power of 9 plus 7. This approach reduces the time complexity to O(n), as we only make a single pass through the array, and the space complexity remains O(1), requiring just a few variables. The key realization here is that the parity of the prefix sum is enough to determine subarray sums, enabling an efficient solution. The advantages of this optimized approach are significant. First, it drastically reduces the time complexity from O(n)² to O(n), making it feasible for larger arrays. Second, it's space efficient, as it doesn't rely on additional data structures and uses only a constant amount of extra space. For these reasons, we chose the optimized approach using prefix sums and modular arithmetic as our solution strategy. Compared to the brute force method, this approach offers a significant improvement in both performance and scalability, which are critical in competitive programming scenarios. Additionally, modular arithmetic ensures the result stays within bounds, as required by the problem constraints. While this method may be less intuitive than brute force and requires a deeper understanding of prefix sums and their properties, it strikes the right balance between efficiency and clarity, making it the most suitable solution for this problem. The goal of this problem is to count the number of subarrays in a given input array where the sum of the elements in each subarray is odd. To tackle this, we start by understanding the brute force approach. First, we generate all possible subarrays by iterating through every starting index and every ending index. For each subarray, we calculate its sum by iterating through its elements. If the sum is odd, we increment a counter. Once all the subarrays have been processed, the counter will hold the total count of subarrays with odd sums, which we return as the result. While this approach is straightforward, it's computationally expensive, and we'll explore why in the next steps. Here, we see the brute force approach translated into pseudocode. We use 3 nested loops. The outer 2 loops iterate over all possible starting and ending indices of subarrays, while the innermost loop calculates the sum of each subarray element by element. Whenever the sum is odd, we increment the count. However, this comes at a significant computational cost. Generating all subarrays involves 2 loops, resulting in O(n)² iterations, and for each subarray, computing its sum adds another loop, giving a total time complexity of O(n)³. This inefficiency becomes apparent when dealing with larger input sizes, say n equals 10,000, as it would lead to impractically high runtimes. Clearly, we need a more efficient approach. To optimize, we can leverage some mathematical properties. A key insight is that a subarray sum is odd if and only if the subarray contains an odd number of odd elements. This allows us to shift our focus from directly summing subarrays to analyzing the parity of their elements. One way to streamline calculations is by using a prefix sum array. With this, the sum of any subarray can be derived in constant time by subtracting the prefix sums at 2 indices. While this reduces the complexity of summing subarrays, it doesn't fully address the inefficiencies of the brute force structure. To scale further, we need a method that eliminates the need to evaluate every subarray individually. This is where we introduce a more advanced idea involving counting prefix sums based on their parity. The optimized solution focuses on counting odd and even prefix sums. Instead of explicitly evaluating every subarray, we use the property that a subarray sum is odd if the difference between the prefix sums at its boundaries is odd. By counting the cumulative number of odd and even prefix sums using a hash map, we can determine how many odd-sum subarrays exist at any point efficiently. The pseudocode demonstrates this approach. We maintain 2 counters, one for odd prefix sums and another for even. As we iterate through the array, we update the prefix sum and check its parity. If the prefix sum is even, we add the current count of odd prefix sums to our result and increment the even count. Otherwise, we add the current count of even prefix sums and increment the odd count. This eliminates the need for nested loops, reducing the time complexity to O(n), which is a significant improvement. The optimized method brings the time complexity down to O(n), making it much more suitable for large input sizes. It achieves this by leveraging the parity relationship between prefix sums, which allows us to efficiently count odd-sum subarrays without explicitly evaluating each one. Additionally, it's robust enough to handle edge cases like arrays with all odd or all even elements, as well as arrays of size 1. By understanding and applying these parity-based relationships, we are able to solve the problem in a highly efficient manner, showcasing the power of mathematical insights in algorithm design. This implementation solves LeetCode problem number 1524 by using a prefix sum approach combined with modular arithmetic. The goal is to count subarrays with odd sums, and we achieve this efficiently by leveraging properties of prefix sums. The number of subarrays function starts by defining a constant mod to handle large results, as required by the problem constraints. Two counters, odd_count and even_count, track the number of prefix sums seen so far that are odd or even. Initially, even_count is set to 1 to account for the empty prefix with a sum of 0, which is even. We then iterate through each number in the input array ARR, updating the cumulative prefix_sum at each step. The parity, odd or even, of prefix_sum determines how we update the result. If prefix_sum is even, adding it to any previous odd prefix sum will result in an odd subarray sum, so we add odd_count to the result. Conversely, if prefix_sum is odd, adding it to any previous even prefix sum will yield an odd sum, so we add even_count to the result. After updating the result, the respective counter, odd_count or even_count, is incremented based on the current parity of prefix_sum. The result is then taken modulo mod to ensure it remains within the required bounds. This approach is highly efficient, with a time complexity of O(n), as we process each element of the array exactly once, and all operations within the loop are constant time. The space complexity is O(1), as we use only a few integer variables to keep track of counts in the prefix sum. In summary, this solution avoids the inefficiency of brute force enumeration of subarrays by relying on prefix sums and modular arithmetic to count odd sums dynamically and in constant space. This makes it well suited for large input arrays, as required by the problem constraints. This is the Java implementation for LeetCode problem number 1524, number of subarrays with odd sum. The logic mirrors the Python implementation, using modular arithmetic to handle large numbers and counters to track odd and even prefix sums. Key differences include type declarations for variables and the use of Java's enhanced for loop to iterate through the array. The final keyword is used for the mod constant, and all operations ensure modularity to prevent integer overflow. To solve this problem, we start with an example where the input array is 1, 3, 5. First, we initialize several variables. The constant mod, which is 10 to the power of 9 plus 7, is used to handle large results. We also define odd_count as 0 and even_count as 1, to account for prefix sums that are odd or even, respectively. Initially, we consider an empty prefix sum as even. Additionally, we initialize prefix_sum to 0 and result to 0. Now, let's iterate through the array. For the first element, 1, we add it to prefix_sum, making it 1, which is odd. Since the prefix sum is odd, we add even_count, which is 1, to the result. This gives us a result of 1. Next, we increment odd_count to 1 to reflect the new count of odd prefix sums. Moving to the second element, 3, we add it to prefix_sum, updating it to 4, which is even. For an even prefix sum, we add odd_count, which is 1, to the result, resulting in 2. Then, we increment even_count to 2. For the third element, 5, adding it to prefix_sum results in 9, which is odd. Since it's odd, we add even_count, now 2, to the result, bringing it to 4. Finally, we increment odd_count to 2. With the iteration complete, we calculate the final output by returning result modulo mod. This ensures that the result fits within the required constraints. For this example, the result is 4. Now, let's consider another example where the input array is 2, 4, 6. Again, we start by initializing the same variables. Mod is set to 10 to the power of 9 plus 7, odd_count begins at 0, and even_count is initialized to 1. prefix underscore sum starts at 0, and result is also set to 0. Next, we iterate through the array. For the first element, 2, we add it to prefix underscore sum, making it 2, which is even. Since the prefix sum is even, we add odd underscore count, which is 0, to the result. The result remains 0. Then, we increment even underscore count to 2. For the second element, 4, adding it to prefix underscore sum gives 6, which is also even. Again, we add odd underscore count to the result, and since odd underscore count is still 0, the result remains unchanged at 0. We then increment even underscore count to 3. Lastly, for the third element, 6, adding it to prefix underscore sum results in 12, another even number. As before, we add odd underscore count, still 0, to the result, leaving it at 0. Finally, we increment even underscore count to 4. At the end of the iteration, we calculate the output as result modulo mod, which is 0 for this example. Now, let's analyze a third example where the input array is 1, 2, 3, 4. As usual, we begin by initializing the necessary variables. Mod is 10 to the power of 9 plus 7, odd underscore count is 0, even underscore count is 1, prefix underscore sum starts at 0, and result is initialized to 0. As we iterate through the array, the first element, 1, is added to prefix underscore sum, making it 1, which is odd. For an odd prefix sum, we add even underscore count, which is 1, to the result, giving us 1. We then increment odd underscore count to 1. For the second element, 2, adding it to prefix underscore sum results in 3, which is odd. Again, we add even underscore count, still 1, to the result, bringing it to 2. We increment odd underscore count to 2. For the third element, 3, adding it to prefix underscore sum updates it to 6, which is even. Since it's even, we add odd underscore count, now 2, to the result, making the result 4. We then increment even underscore count to 2. For the fourth and final element, 4, we add it to prefix underscore sum, resulting in 10, which is even. Since the prefix sum is even, we add odd underscore count, which is 2, to the result. This brings the result to 6. Finally, we increment even underscore count to 3. At the end of the iteration, we calculate the output as result modulo mod. For this example, the final result is 6. The time complexity of this solution is O(n), where n represents the length of the input array. This efficiency comes from the fact that we use a single loop to traverse the array. During each iteration, we perform a handful of constant time operations. For instance, updating the prefix sum, determining if it's odd or even using the modulo operator, and adjusting the counts of odd and even prefix sums are all O(1) operations. Similarly, updating the result and applying a modulo operation to keep it within bounds also take constant time. Since these operations are repeated for each element in the array, and the loop completes exactly n iterations, the overall time complexity is O(n). What's important to note is that this efficiency holds true for all cases, whether the array has all odd numbers, all even numbers, or a mix, because the loop always processes the array in a single pass. Thus, the time complexity remains O(n) in the best, average, and worst cases alike. Now, let's discuss the space complexity of the solution, which is O(1). This is because the algorithm only uses a constant amount of extra space, regardless of the size of the input array. Specifically, we use a few integer variables like prefix underscore sum, odd underscore count, even underscore count, result, and a constant mod. Each of these variables occupies a fixed amount of memory, and their count does not scale with the input size. Additionally, the solution does not involve any additional data structures such as arrays, lists, or dictionaries. The input array itself is neither modified nor duplicated, so there's no extra space allocated for it. As a result, the total space complexity of this solution is constant, or O(1). To understand the efficiency of this optimized approach, let's compare it with a brute force solution. In a brute force method, we would generate all possible subarrays of the input array and calculate their sums to check if they are odd. This is computationally expensive because the number of subarrays in an array of length n is approximately n squared. Generating all these subarrays alone takes n squared time, and computing the sum of each subarray adds another layer of complexity. In the worst case, summing up to n elements for each subarray results in an overall time complexity of n cubed. By contrast, the optimized approach avoids explicitly generating subarrays. Instead, it leverages prefix sums and the counts of odd and even prefix sums to directly determine the number of odd subarrays ending at each index in constant time per element. This reduces the time complexity from n cubed to n, making it significantly more efficient. Finally, let's provide a mathematical justification for the big O analysis. In the optimized solution, the loop that processes the array runs for exactly n iterations, and during each iteration, only O1 operations are performed. Since there are no nested loops or recursive calls, the overall time complexity is n. On the space side, the algorithm uses a fixed number of variables, and no additional space is used that depends on the size of the input. This leads to a space complexity of O1. To summarize, the optimized solution has a time complexity of n and a space complexity of O1, which is a significant improvement over the brute force approach, where the time complexity is n cubed, and the space complexity is still O1. This demonstrates the efficiency and scalability of the optimized solution over the brute force method. When tackling this problem, there are several common mistakes to watch out for. First, not handling large input sizes efficiently is a major issue. A brute force approach that generates all subarrays and calculates their sums can have a time complexity of n cubed, which is impractical for large arrays, such as when n exceeds 1000. This can easily lead to time limit exceeded errors. Next, overlooking edge cases is another frequent pitfall. For instance, arrays with only one element, or arrays containing exclusively even or odd numbers, need special consideration. Failing to account for these cases can result in incorrect outputs or runtime errors. Another common misunderstanding relates to the parity of sums. Simply having odd numbers in a subarray doesn't guarantee an odd sum. The sum's parity depends on the count of odd numbers in the subarray. Additionally, incorrect handling of modular arithmetic is a frequent issue. If the problem involves modulo operations, forgetting to apply the modulo at every step can lead to integer overflow or inaccurate results. Lastly, many people skip prefix sum optimizations, which is a missed opportunity to reduce redundant calculations. Without leveraging prefix sums, the solution's time complexity can remain quadratic, whereas it could be improved to linear time with this optimization. Now, let's focus on insights that can help you stand out during interviews. A key insight is understanding how odd and even numbers interact. For example, odd plus odd results in even, while odd plus even gives odd. Recognizing and leveraging these patterns can guide you toward an efficient solution. For optimization, always consider techniques like prefix sums, sliding windows, or hash maps for problems involving subarrays or ranges. These methods are often the key to improving performance. During an interview, it's also important to communicate trade-offs. Explain why a brute force solution is inefficient and highlight the thought process that leads you to a better approach. This shows depth in problem solving. Additionally, make sure to test your solution against edge cases explicitly. For example, arrays with only one element or those made entirely of even or odd numbers. This demonstrates thoroughness and attention to detail to the interviewer. Finally, it's helpful to study related problems. For instance, problems like LeetCode 560, subarray sum equals k, or LeetCode 1248, count number of nice subarrays, share overlapping concepts with this problem and can deepen your understanding of efficient techniques. Let's explore alternative approaches to solving this problem. One approach is using prefix sums along with odd count tracking. This method requires extra space for storing the prefix sum on a hash map, but in return, it reduces the time complexity to n. The main idea here is to maintain a cumulative sum while keeping track of the counts of odd and even sums to calculate the number of odd subarray sums efficiently. Another option is the sliding window approach. This method is often faster for fixed-length subarrays since it dynamically adjusts the window to maintain certain properties, such as ensuring the sum remains odd. However, it's less suitable for variable-length subarrays, which is a trade-off to consider. Lastly, dynamic programming offers another alternative. A DP-based solution can be optimal in terms of time complexity, but it comes with its own challenges, such as careful state management, which can make the implementation more complex. In this approach, you would use a DP array to store intermediate results, like the number of odd subarrays ending at each index, enabling efficient computation of the final result. Thank you for joining this session. Today, we learned how to solve the number of subarrays with odd sum problem efficiently, explored key concepts like prefix sums and modular arithmetic, and discussed best practices for optimizing solutions. If you enjoyed this, be sure to like, share, and subscribe for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!